Here's another solids of revolution washer example. And in this problem, we have the region bounded by the line y equals x, and the parabola y equals 1/3 x squared is revolved about the line y equals -2. And we want to find an integral that can be used to compute the volume of the resulting solid. Here's an illustration of the problem. The line y equals x and the parabola y equals 1/3 x squared intersect at the origin and at the point 3, 3. So our region is bounded by those two curves, and we're going to revolve this region about the line y equals -2. So we have a nice picture here. The outer part of this is the frustum of a cone. The inner part, well, it looks awfully much like a bugle or horn of some kind. And we can approximate the volume of this object using washers. And so 4 washers look as shown. And if we add up the volume of those 4 washers, we're going to get a crude approximation to the volume of the solid. Of course, we get a better approximation if we use more washers. So here we see this, and you see the outer part of this is part of a cone. We can have another view, and we can see that the inner part of this looks like a bugle. Here's a cross section. You can see here we have essentially the line segment and the paraboloid, well, parabola illustrated here. Here we have an illustration of the ith washer. So I here is going from 1 to 14. And in general, we'll let I go from 1 to n. But now this washer here is centered at the line y equals -2. And I see that it has an outer radius and an inner radius. So the inner radius, we're going from this point on the parabola down to line y equals -2. So that's my inner radius right there. And then my outer radius, I'm starting up here at the kind of upper part of this picture where the washer touches the line segment. So I'm going here, and I'm going from that line all the way down here, and that gives me my outer radius. And we have a certain thickness here, a little change in x here, which kind of indicates that we're going to have x to be our variable of integration. But I want the volume of this washer, and it's a very simple formula. We just use the cross-sectional area times the thickness. But the area, the cross-sectional area here is just the difference between the areas of two circles, my outer circle and my inner circle. So I have pi capital R sub I squared minus pi little r sub I squared, all times the thickness is change in x. So first we consider the outer radius, and the outer radius is going to be the starting on the line segment here, where the washer touches the line segment, and going down to this line y equals -2. So here's my outer radius here. And then the point on this line segment is x sub I, y sub I, but I wrote these down here for illustration. And you can see that we have y sub I going from the line segment to the x-axis, but then we have to go 2 more down to hit the line y equals -2. So evidently from our picture, we have our y sub I plus 2 is r sub I, which of course we can rewrite as r sub I is y sub I plus 2. And I can write this r sub I as x sub I plus 2 because that on that line segment y equals x, so x sub I is y sub I. And this is what we want because we want things in terms of x. So here is our outer radius. Okay, for the inner radius, we're starting on the point on the parabola that hits this washer here, touches it. And we're going down to the line y equals -2. So this, my inner radius, is right here. And I notice again, this point of the parabola is x sub I, y sub I. So I'm going from the parabola down to the x-axis. But then I have to go 2 more units down to get to the line y equals -2. So looking at our picture, we see that our r sub I is y sub I plus 2. But this is just 1/3 x sub I squared plus 2, because that point is on the parabola, y equals 1/3 x squared. So now we have our inner radius right here. And now we consider our volume. So we're calling our ith volume here. We have the cross-sectional area times the thickness, but we wrote both these radii in terms of x sub I, so we get this expression. So this is our volume of the ith washer. And basically, if I add up n of these, I'm going to have an approximation to the actual volume. And we can write this in sigma notation if we like. I have the sum I equals 1 to n. And then what we do, we have this expression. What we do is kind of interesting. We let n go to infinity. So we have more and more of these washers, and our change in x is going to get smaller and smaller. But in the limit, we get something, the limit of these Riemann sums, we get something called a definite integral. And this is going to give us the exact volume. So here I'm going from 0 to 3 because that's what x is going from in our region. And then I have this similar expression here as I had to in the sigma notation. It's just my x sub i's here are replaced by x's. And my change in x here corresponds to the differential of x here. And if I want to, I could work this out. It's not that complicated. It's a little tedious by squaring things out and then using the power rule and the fundamental theorem of calculus. And we can get an exact answer. And again, I say this every time, it's amazing because we found this volume of this solid, this kind of strange object, just using volumes of washers. And that's that. Thank you.